Welcome back. Over the past hour, we've explored your journey into physical AI engineering, uncovered what the industry is really like, heard fascinating stories from real world deployments, and followed you through a typical workday. Now let's look ahead. Artificial intelligence is evolving rapidly. Robots are becoming more capable. Sensors are becoming more affordable. Edge computing is becoming more powerful. Simulation technologies are becoming increasingly realistic. What does the future of physical AI actually look like?
I believe we're entering one of the most exciting periods in engineering history. For decades, machines were designed to repeat predefined tasks. If something unexpected happened, they usually stopped and waited for human intervention. The next generation of intelligent machines will be very different. They won't simply execute instructions. They'll perceive their surroundings, understand changing environments, reason about different possibilities, collaborate with people, and continuously improve through experience. The future of physical AI is about creating machines that can safely adapt, not just automate.
Many people still wonder what exactly makes physical AI different from traditional artificial intelligence? How would you explain the difference?
Traditional AI mainly processes digital information. It answers questions, analyzes documents, recommends products, or generates text and images. Physical AI connects intelligence directly to the physical world. Imagine asking an AI assistant to summarize a report. Now compare that with a warehouse robot carrying heavy equipment, a surgical robot assisting a doctor, or an autonomous tractor harvesting crops. Those systems must perceive the environment, understand motion, avoid obstacles, react within milliseconds, and make safe decisions. Physical AI combines intelligence with action. That's what makes it unique.
We've already seen robots in factories for many years. How will the next generation be different?
Future robots won't simply repeat fixed sequences of movements, they'll become adaptive. Imagine a manufacturing robot assembling products even when component positions vary slightly. Imagine warehouse robots automatically reorganizing their routes when shelves are moved. Imagine agricultural robots identifying unhealthy crops individually instead of treating entire fields. Instead of relying entirely on predefined programming, they'll continuously interpret their surroundings and adjust their behavior. That flexibility is one of the biggest changes physical AI will bring.
Artificial intelligence seems to be influencing every engineering field. How is AI reshaping robotics?
AI is becoming the intelligence layer of robotic systems. Instead of programming every movement manually, engineers increasingly teach robots through data, demonstrations, simulations, and reinforcement learning. Computer vision enables robots to recognize objects. Sensor fusion improves environmental awareness. Machine learning recognizes patterns. Reinforcement learning helps robots improve through repeated experience. Large AI models help robots understand language and human instructions. Embedded AI allows all these capabilities to run directly inside intelligent machines. Together, these technologies create robots that are more adaptable than ever before.
You've mentioned reinforcement learning several times. How important will it become?
Extremely important. Imagine teaching a robot to stack objects. Instead of writing detailed instructions for every possible situation, the robot practices thousands or even millions of attempts inside simulation. It gradually discovers strategies that work best. As simulation environments become more realistic and computing power continues growing, reinforcement learning will enable robots to learn increasingly complex skills before entering the real world. That dramatically reduces development time and improves deployment safety.
Simulation and digital twins also seem to be growing rapidly. Where do you see them heading?
Today's digital twins already represent machines, robots, factories, and production systems. Tomorrow's digital twins will become continuously connected to real operations. Imagine creating a virtual copy of an autonomous warehouse. Every robot, every conveyor, every sensor, every package. The digital twin receives live operational data. Engineers can test software updates, optimize traffic flow, evaluate robot behavior, predict maintenance requirements, and identify bottlenecks before changing the physical environment. Simulation becomes an everyday engineering tool rather than an occasional testing platform.
What role will human robot interaction play in the future?
A very significant one. Robots won't replace people in most industries. They'll increasingly become teammates. Manufacturing workers will collaborate with intelligent robotic assistants. Healthcare professionals will work alongside surgical and rehabilitation robots. Agricultural workers will supervise fleets of autonomous farming equipment. Construction teams will coordinate with intelligent machines. For these partnerships to succeed, robots must become easier to understand, easier to trust, and easier to communicate with. Human robot interaction will become just as important as artificial intelligence itself.
Safety must continue evolving too.
Absolutely. As robots become more autonomous, safety becomes even more critical. Future physical AI systems will continuously monitor their own health, detect sensor failures, estimate uncertainty, predict unsafe situations before they occur, automatically reduce operating speed near people, request human assistance. When confidence becomes too low, safety will increasingly become proactive rather than reactive.
Many learners listening today are probably wondering about career opportunities. What kinds of new jobs do you think will emerge?
We are already seeing tremendous growth in roles such as physical AI engineer, robotics AI engineer, autonomous systems engineer, computer vision engineer, sensor fusion engineer, reinforcement learning engineer, embedded AI engineer, robot software engineer, human robot interaction specialist, digital twin engineer, AI safety engineer, intelligent manufacturing engineer, autonomous mobility engineer, edge AI engineer, robotic systems architect. As intelligent machines become more common across industries, demand for professionals who understand both AI and robotics will continue growing rapidly.
What about entrepreneurship? Is this a good time to build a physical AI startup?
I believe it's one of the best times in history. Almost every industry faces labor shortages, safety challenges, repetitive work, quality control requirements, or operational inefficiencies. Physical AI creates opportunities to build intelligent warehouse, robots, AI-powered inspection systems, autonomous agricultural machines, smart healthcare assistants, drone inspection platforms, collaborative industrial robots, AI-powered logistics systems, construction robotics, autonomous cleaning and maintenance robots, intelligent service robots. The opportunities are enormous because industries increasingly need machines that can adapt rather than simply automate.
Where do the best startup ideas usually come from?
From observing real world problems, spend time inside factories, visit warehouses, talk to farmers, observe hospitals, watch logistics operations, understand repetitive, dangerous, or physically demanding tasks. The best startup ideas don't begin with artificial intelligence, they begin with problems that intelligent machines can solve safely and effectively. Technology becomes valuable only when it improves people's lives or helps organizations operate more efficiently.
Many students feel overwhelmed because this field combines AI, robotics, electronics, embedded systems, computer vision, simulation, and control systems. How should they approach learning?
One step at a time. Begin with programming, understand mathematics, study robotics fundamentals, learn computer vision, understand sensors and sensor fusion, explore machine learning, study reinforcement learning, learn embedded AI, practice simulation, understand human robot interaction. Finally, learn how all these technologies integrate into complete intelligent systems. Don't try to master everything simultaneously. Build one capability at a time. Eventually, you'll understand how they all connect.
Before we conclude today's discussion, if you had to describe the future of physical AI in one sentence, what would you say?
I'd say this: the future of physical AI is about creating intelligent machines that can safely perceive, learn, collaborate, and adapt in the real world, working alongside people to solve problems that were once impossible to automate.
That's an inspiring vision. Today's discussion has shown us that physical AI isn't simply another branch of artificial intelligence. It's becoming the bridge between intelligent software and the physical world, enabling smarter factories, autonomous mobility, precision agriculture, healthcare innovation, intelligent logistics, and next generation robotics. In our final segment, we'll ask one last question. If you could go back and advise yourself as a third year engineering student, what would you do differently? We'll discuss the skills worth investing in, technologies to prioritize, common mistakes to avoid, startup advice, and one final message for everyone beginning their physical AI journey. Stay with us for the final chapter of today's conversation.